Hey there, and welcome. Today, we are going on a journey into the invisible forces that are, well, literally powering our world. We're going to peel back the layers on a concept that's key to everything from the battery in your phone to the neurons in your brain. We're talking about electric potential. So, let's jump right in. This sounds like a trick question, right? But the answer actually gets to the very heart of physics. In both cases, you're doing work against an invisible force field to store up energy. With the book, it's gravity. With your phone, it's electricity. But that core idea, it is exactly the same. So here's our game plan. We're going to start with a universal rule about energy that applies to everything. Then we'll see how that rule plays out with electric charges. After that, I'm going to show you a master shortcut called potential. And finally, we'll put it all together and solve some real problems. Okay, so if we want to really get a handle on energy in the world of electricity, we have to start with a concept that you see everywhere in physics, the idea of work. Now, this equation right here, the Work-Energy Theorem, this is our master key. It's the thing that connects the work you do on any system to the change in that system's energy. It doesn't matter if you're lifting a dumbbell or pushing an electron around. This rule always applies. So, here's the bottom line. When some outside force does work on a system, that energy has to go somewhere, right? It can't just disappear. It either makes the object move faster, that's a change in kinetic energy, or it gets stored up as potential energy, just waiting to be used later. All right, so how does this big universal rule actually connect to electricity? Well, now we're taking that idea from the world we can see, like lifting boxes, into the invisible world of electric charges and fields. Think about it this way. Trying to push two positive charges together, it's tough, right? They naturally repel each other. So all that effort, all that work you're putting in, it gets stored in the electric field between them. It's just like when you compress a spring. You're storing energy that's ready to snap back out. And this is a perfect picture of what we're talking about. On the left, you've got this initial setup of charges, and it has a certain amount of energy stored in it. Then, on the right, you see what happens after we've done some work to move those charges into a new spot. That work we did directly changed the system's stored or potential energy. This little equation right here is our anchor. It tells us exactly how much energy we've packed into the system. The external work done, that's Wx, is simply the difference between the final potential energy, U final, and whatever the initial potential energy was, U initial. Simple as that.
Okay, now we get to the really cool part, the big aha moment that just simplifies everything. Instead of always talking about the energy between two specific charges, what if we could talk about the energy of a point in space itself? This, my friends, is the concept of electric potential.
And that's the key question, isn't it? Calculating the work for every single pair of charges would be a total nightmare. We need a smarter way to do this. How can we map out the energy landscape that a source charge creates even before we drop another charge into it? And here it is, the elegant solution. Electric potential, which we call V, is just the work done per unit of charge. And a coulomb is just our standard unit for measuring charge, kind of like a kilogram for mass. So what we're really asking is, how much work would it cost to bring one standard-sized positive charge to this exact spot? So from now on, when you hear someone say 1 volt, what you should really hear is 1 joule of energy per 1 coulomb of charge. It's a way of measuring the energy that's just baked into a point in space, all because there's a charge somewhere nearby creating a field. I absolutely love this analogy. Think of electric potential as putting a little price tag on every single point in space. That price tag tells you how much energy it's going to cost per coulomb to bring a charge to that location. And here's the key. That price is there whether or not a customer, our little test charge, ever shows up. And this is exactly why potential is our master shortcut. Just look at this. To figure out the work it takes to move a charge Q from point A to point B, we don't have to care about the crazy winding path it took anymore. All we need to know is the difference in potential, the difference in the price tag between where it started and where it ended. The work is just the charge times that potential difference. So much easier. All right, that's enough theory. Let's actually put this powerful shortcut to work. We're going to see how this idea makes solving physics problems, well, incredibly straightforward. Okay, first up, a classic problem. We've got a source charge, and we just want to know the potential, that energy price tag, at a specific spot, point P, which happens to be 10 meters away. And the solution is just beautiful. We just plug our values, the size of the charge and the distance, straight into our formula for potential. A quick calculation, and bam, the potential at point P is 8,100 volts. That's its price tag. Done.
Let's try another one, this time using our master shortcut. Okay, so we know how much work we did, 50 joules, we know the charge we moved, 2 coulombs, and we know the potential where we started, minus 10 volts. The question is, what's the potential at our final destination?
We just bust out our potential difference formula, W equals Q delta V. We can plug in the work and the charge, solve for the change in potential, and from there, it's easy to find the final potential. And the answer is positive 15 volts. See how powerful that shortcut is? We didn't need to know anything else.
Okay, for our next problem, we're going to try to do something that sounds flat out impossible, adding up an infinite number of things. And to do that, we need a special trick from our math toolkit called a geometric series. Now, the main idea is actually pretty simple. If you have an endless list of numbers, and each one is getting smaller by the same fraction, you can actually find their total sum with one neat little formula.
And this is the perfect reason why we need that tool. I mean, how on earth do you find the total potential from an infinite line of charges? It seems like it should be infinity, right? But because the charges alternate signs and they get farther and farther away, their potentials happen to form exactly the kind of infinite series we just talked about. We use our formula, we sum up infinity, and we get a single finite number. Just amazing.
Which brings us to our final and maybe most mind-bending question of the day. We've been talking about potential as the energy price tag. So is it possible to have a spot where the price is zero, but there's still a really strong force, a powerful electric field, pushing or pulling on any charge you put there? And the answer is a huge, resounding yes. Just look at this hexagon. Right in the very center, the positive and negative potentials, which are just numbers, we call them scalars, that all perfectly cancel each other out. They add up to zero. But the electric field forces are vectors. They have direction. And if you look closely, those force arrows are all adding up, creating a strong net field pointing to the right. So you can absolutely have a point with a $0 price tag that still gives a charge a very powerful push. It's a really crucial distinction and a fantastic place to end our journey into this invisible and absolutely fascinating world of electric potential.